the universe should not be this quiet. The Milky Way contains hundreds of billions of stars. Many are surrounded by planets, and many formed long before Earth existed. NASA's archive now contains more than 6,000 confirmed worlds beyond our solar system, but those discoveries represent only the planets our instruments have been able to find. The true number in the galaxy is expected to be vastly larger. Rocky planets are no longer considered unusual. Water exists in comets, icy moons, and clouds between the stars. Astronomers have also found carbon-rich molecules in meteorites and in enormous regions of gas and dust where new planetary systems are forming. None of this proves that life begins easily. It does show that the raw materials and possible locations are spread throughout space. With so many opportunities, and with billions of years available, intelligence might have appeared somewhere else long before humans began looking upward. Even one civilization that learned to travel between nearby stars could have left evidence behind. We might expect a radio beacon, a repeating laser pulse, an artificial probe, unusual structures collecting the energy of a star, or chemicals in a distant atmosphere that nature would struggle to produce. So far, no example of any of these has been confirmed. By the end of tonight, you are going to understand what humanity has actually searched, what the silence can and cannot tell us, and why nearly every serious explanation leads to a troubling consequence. Life may be extraordinarily difficult to begin. Complex intelligence may be a rare accident. Civilizations may appear at different times and miss one another completely. Some may become quiet before anyone can hear them. Others may never survive long enough to spread beyond their home world. Before we continue, if you enjoy calm journeys through the largest questions in space, you can like the video and subscribe. It helps this channel continue making long documentaries for nights like this. The silence we are discussing has a precise meaning. It does not mean that astronomers have examined every planet and found it empty. We cannot yet see the surfaces of Earth-sized worlds across most interstellar distances. We cannot monitor every star continuously, listen to every radio frequency, or recognize every form that unfamiliar technology might take. A message could pass Earth while our telescopes are pointed elsewhere. A transmitter could be too weak, too brief, too distant, or aimed in another direction. A civilization could communicate through a method we have not invented. Our search has covered only a small part of an enormous range of possibilities. Even so, the missing evidence matters. Radio telescopes have examined nearby stars across millions of frequency channels. Optical instruments have searched for brief laser flashes. Infrared surveys have looked for the heat that enormous technological systems might release. Spacecraft have photographed planets, moons, asteroids, and the outer regions of our own system. These searches have revealed remarkable natural objects and processes, but no confirmed technological trace from another civilization. That absence can be interpreted in several ways, and the possibilities do not all point in the same direction. Perhaps there is almost no one to find. Perhaps the galaxy contains life that never becomes complex enough to build machines. Technological societies might exist while remaining detectable for only a few centuries. They may communicate in narrow beams, turn inward toward compact forms of existence, or remain hidden by choice. Humanity may also have begun searching far too recently, with instruments that are still too limited to detect what is already there. The frightening part is not that one of these ideas has been proven. None of them has. The frightening part is that each surviving explanation changes the meaning of the silence. If life almost never begins, Earth may be far more unusual than we understand. If intelligence is common but short-lived, the quiet sky may contain a warning about the future of technological species. If civilizations remain hidden, then silence may be something they learned to preserve. If distance and timing keep every society isolated, the galaxy could contain many minds that never learn of one another. To understand which possibilities deserve serious attention, we have to begin with the part of the mystery that makes the silence hardest to dismiss. The Milky Way did not begin when Earth formed. It had already existed for billions of years, producing stars, planets, and possible homes for life, long before our world appeared. By the time Earth began to form, the Milky Way had already been changing for about 9 billion years. The universe itself is approximately 13.8 billion years old. Our galaxy began taking shape roughly 13.6 billion years ago, when enormous clouds of hydrogen and helium started collapsing under gravity. Some of the Milky Way's oldest known stars formed during this early period, while the galaxy was still assembling from smaller clouds and young stellar systems. Earth arrived much later. The solar system formed about 4.57 billion years ago from a rotating cloud of gas and dust. Most of that material gathered at the center to form our star. The remaining matter flattened into a broad disk where grains collided, stuck together, and gradually built the planets, moons, asteroids, and comets. That material had a long history before it reached our neighborhood. The first stars formed mainly from hydrogen and helium, the two lightest elements. They contained almost none of the carbon needed for organic chemistry, the oxygen found in water, the silicon that forms much of a rocky planet's crust, or the iron that collects inside planetary cores. Astronomers call elements heavier than hydrogen and helium metals, even when those elements would not normally be described as metals on Earth. Stars manufactured many of these heavier elements through nuclear fusion. Deep inside a star, enormous pressure forces lighter atomic nuclei together and produces heavier ones. Massive stars can continue this process until elements near iron are created in their cores. When some massive stars reach the ends of their lives, they explode as supernovae. These explosions throw newly formed material across interstellar space. Other elements escape through stellar winds, while some of the heaviest are produced when neutron stars collide. A neutron star is the extremely dense collapsed core left behind after certain massive stars explode. New stars eventually form from clouds enriched by the remains of older stars. Their planets inherit the same material. Astronomers call this gradual build-up galactic chemical evolution. Each generation changes the ingredients available to the generations that follow. The earliest period of the Milky Way may therefore have offered fewer opportunities for rocky, chemically complex worlds. Conditions improved as stars completed their lives and returned newly formed elements to space. By the time our solar system appeared, several generations had already enriched the galaxy. Some rocky planets may be much older than Earth, while still containing abundant carbon, oxygen, silicon, and iron. The exact age range remains uncertain because astronomers cannot date most exoplanets with the precision available for objects in our own system. Even so, confirmed planetary systems exist around stars several billion years older than ours. A world that formed 2 billion years before Earth would have received 2 billion additional years for oceans to settle, climates to stabilize, chemistry to develop, and evolution to proceed. A 4 billion year head start is almost as long as the entire history of life on our planet. Recorded human history covers only several thousand years. 1 billion years contains that span well over 100,000 times. A civilization could spend millions of years developing technology during such a head start. Vast stretches of time would still remain before the first humans appeared. Biology elsewhere would not need to follow Earth's timetable. Life might begin later, progress more slowly, remain microbial, or never appear at all. The importance of the head start comes from the number of opportunities. Across hundreds of billions of stars, some worlds may have begun their biological histories far earlier than ours. If even one of those older worlds produced a civilization capable of surviving for a small fraction of its planet's history, its machines and signals could predate every human invention by millions or billions of years. A civilization with that much time would not need to break the speed limit of light. Patient travel between nearby stars, repeated often enough, could leave evidence across much of the galaxy. The Milky Way stretches for more than 100,000 light-years from one side of its stellar disk to the other. That scale sounds like a permanent barrier, especially when the nearest star system is already about 4.24 light-years away. Yet, neighboring stars are usually separated by distances of only a few light-years, and a journey does not have to cross the entire galaxy in one attempt. Imagine a spacecraft moving at 1% of the speed of light. That is far beyond anything humans have built, though it remains comfortably below the limits set by relativity. At that speed, a voyage of 4 light-years would take about 400 years. A trip of 10 light-years would require roughly 1,000 years. Those durations are enormous beside a human lifetime. They become much smaller when placed inside a history measured in millions of years. Suppose one inhabited system sends missions towards several nearby stars. Some destinations may prove unsuitable, while others may contain asteroids, moons, or planets with useful raw materials. A successful settlement could spend centuries building habitats and developing its own spacecraft. Once ready, it could send missions toward additional stars. The process would spread as a branching network. Each established system becomes a new point of departure, so the original world does not need to launch every mission itself. One settled system might lead to 2 more. Those destinations could later produce 4 additional branches, followed by a wider wave moving through the galactic disk. The exact growth would never remain perfectly regular. Stars move around the galaxy. Settlement attempts could fail. Civilizations might pause expansion for long periods, or choose only certain destinations. Even with these delays, repeated branching can cover territory far faster than a single vessel following one continuous route. Researchers have built computer models to explore different versions of this process. The results vary because the assumptions vary. Faster ships, short construction periods, and frequent launches can produce expansion across much of the Milky Way in a few million to a few tens of millions of years. Slower migration, selective settlement, and long pauses can stretch the process across hundreds of millions of years. Some cautious models allow it to continue for billions. Every one of those timescales fits inside the history available to planetary systems older than ours. A separate idea replaces settlers with machines. In 1966, the Hungarian-born mathematician John von Neumann's work on self-reproducing automata inspired later discussions of robotic probes that could copy themselves. These are now commonly called von Neumann probes, although he did not design an interstellar spacecraft. A probe of this kind would arrive in a new system and search for metals, carbon, silicon, and other materials in asteroids or small moons. Automated factories would process those resources into replacement parts and new spacecraft. The copies would then depart for different stars, while the original probe continued observing or manufacturing. No machine with this ability exists today. Building one would require reliable autonomous mining, manufacturing, navigation, and repair across centuries without human assistance. A copying error could disable later generations, and uncontrolled replication would create serious risks. The concept still matters because it shows how exploration could continue without transporting biological passengers or maintaining a continuous political empire. Even modest speed becomes powerful when machines can reproduce at each destination. At 1% of light speed, travel between nearby stars may take centuries. If a probe then spends another few hundred years building copies, each step might require roughly 1,000 years. 10,000 such steps would fit inside 10 million years, while thousands of branches could be operating at the same time. The Milky Way's size remains extraordinary. Its age is even more important. A wave that needed 100 million years would consume less than 1% of the galaxy's lifetime. A process lasting 1 billion years could have finished several times during the head start available to some older planetary systems. That does not show that any civilization has expanded this way. It shows that ordinary travel speeds and repeated branching leave enough time for the possibility. If such a wave ever crossed our region, its traces might include abandoned probes, altered star systems, artificial energy use, or settlements that continued long after the original civilization changed. The apparent absence of those traces turns a calculation about travel into the simple mystery that Enrico Fermi expressed over lunch. That contradiction entered scientific history during the summer of 1950 at the Los Alamos Laboratory in New Mexico. Physicist Enrico Fermi was walking to lunch with several colleagues, including Edward Teller, Emil Konopinski, and Herbert York. Their conversation moved through recent newspaper stories about flying saucers and then toward the possibility of travel between stars. A cartoon in the New Yorker had jokingly blamed missing public trash cans on visiting aliens, which gave the group one more reason to talk about extraterrestrial life. Accounts of the lunch were written down years later, so some details differ between witnesses. The remembered moment is remarkably consistent. In the middle of the discussion, Fermi suddenly asked, "Where is everybody?" He did not publish a paper presenting a formal Fermi paradox. The name came later, as other researchers developed the reasoning behind his short question. The galaxy contains an enormous number of stars. Many are older than our solar system. Travel between neighboring systems appears physically possible at speeds below that of light, and repeated settlement could spread over immense distances during a small fraction of galactic history. Yet Earth shows no accepted evidence that such an expansion has reached this region. No confirmed alien probe has been recovered. Astronomers have identified no engineered star system and received no verified transmission from another civilization. The expectation points toward visible activity, while observation continues to show natural planets, natural stars, and unexplained events that never become proof. The word paradox can make this sound like a logical impossibility. Scientists use it more loosely here. The Fermi paradox is a conflict between a set of plausible assumptions and the evidence currently available. Resolving it requires at least one assumption to change. Perhaps suitable planets are less common than they appear. Life may begin only under unusual chemical conditions. Complex cells could require a rare evolutionary event. Intelligence might emerge frequently without producing technology. A civilization may also remain detectable for such a short period that two societies almost never overlap. Frank Drake gave these possibilities a more organized form 11 years after Fermi's lunch. In November of 1961, 10 researchers gathered at the National Radio Astronomy Observatory in Green Bank, West Virginia. The meeting was one of the first scientific conferences devoted specifically to the search for intelligent life beyond Earth. Drake needed a practical way to arrange the discussion, so he wrote an equation containing 7 factors. It begins with the rate at which stars form in the Milky Way. That value is combined with the fraction of stars that possess planets. The next factor estimates how many worlds in each planetary system might provide conditions suitable for life. From there, the equation enters territory that remains far less certain. It asks how often life actually begins on a suitable world, how often that life develops intelligence, and how often an intelligent species creates technology that can be detected across space. The final factor is the average length of time that a civilization remains detectable. Each factor is multiplied by the others. This matters because one very small value can reduce the final result sharply. A galaxy may produce many habitable planets, while a tiny probability for the origin of life leaves almost all of them sterile. Intelligence could be common, while an average detectable lifetime of only a few decades produces very little overlap. The final lifetime term is especially powerful. Suppose new technological civilizations appear at a steady rate, but each broadcasts recognizable signals for only 100 years. Very few may be active at the same moment. Extend that lifetime to 1 million years, and the number present together rises enormously without changing any of the biological terms. Astronomy has made progress on the opening parts of Drake's equation. Researchers now know that planets are common, including small rocky worlds. Measurements of exoplanet atmospheres and orbits continue to improve. The later factors still rest on a sample of one inhabited planet and one technological species. Earth confirms that the full sequence can occur. It does not reveal how often each step succeeds elsewhere. The Drake equation, therefore, provides a map of the uncertainty. The silence may begin with planet formation, continue through biology, or appear only after technology develops. Determining where the missing civilizations went first requires understanding how much of the sky humanity has truly examined. That map of uncertainty became a real experiment in the spring of 1960 in the wooded hills of Green Bank, West Virginia. Frank Drake was 29 years old and working at the National Radio Astronomy Observatory. He had recently become interested in a practical idea that had once belonged mostly to speculation. If another civilization used radio technology, its transmissions might cross interstellar space and arrive at Earth as a measurable signal. Drake used the Howard E. Tatel radio telescope, an 85-foot dish completed only a short time earlier. The telescope stood in a valley, protected from much of the radio noise produced by cities. Its metal surface collected faint radio waves and focused them into a receiver, much as an optical telescope gathers visible light. The experiment was called Project Ozma, after the princess in the Land of Oz stories. Drake selected two nearby stars, Tau Ceti and Epsilon Eridani. Both are visible without a telescope under dark skies, and both lie roughly 11 light-years from Earth. Their distances meant that any signal received in 1960 would have left its source around 1949. The two stars also appeared reasonably similar to our own star by the standards of the time. Tau Ceti is a quiet yellow star, slightly smaller and cooler than ours. Epsilon Eridani is a younger orange star with stronger magnetic activity. Astronomers did not yet know whether either star possessed planets. The first confirmed planets around ordinary stars would not be announced until 1995. Drake tuned the receiver near a frequency of 1,420 MHz. This corresponds to radio emission from neutral hydrogen, the simplest and most abundant element in the universe. Hydrogen atoms naturally emit radio energy at a wavelength of about 21 centimeters when the orientation of an electron changes relative to the proton in the atom. A scientifically capable species might recognize that frequency as a universal landmark. The idea did not require two civilizations to share a language or a calendar. Both could measure the properties of hydrogen. Project Ozma searched for signals concentrated inside an extremely narrow frequency range. Many natural radio sources spread energy across broad bands. A transmitter designed for communication can place much of its power into a narrow channel, making it stand out against the surrounding noise. The receiver examined one channel only about 100 Hz wide at a time. 100 Hz is a tiny slice of the radio spectrum. Modern searches can process millions or billions of channels at once, but Drake's equipment relied on analog electronics, a paper chart recorder, and a loudspeaker. He watched a pen trace the changing signal strength while listening for tones that did not resemble ordinary cosmic static. During an early observation of Epsilon Eridani, a strong signal suddenly appeared. It was exciting enough that Drake quickly pointed the telescope away from the star. The signal remained. That behavior showed that it was coming from somewhere near Earth rather than from the distant system. The most likely source was radar from an aircraft passing through the region. That false alarm revealed a difficulty that still shapes the search today. Human technology fills parts of the radio spectrum with television carriers, navigation systems, satellites, radar, and communications equipment. A distant signal must be separated from all of them. Project Ozma observed the two stars for about 150 hours over several months. It found no confirmed extraterrestrial transmission. The result placed no meaningful limit on the rest of the galaxy. Only 2 targets had been examined, through one narrow portion of the spectrum, during a very small number of hours. Even so, the experiment changed the subject permanently. A question discussed over lunch had become something that could be tested with instruments. Humanity had begun listening, although the opening was barely wider than a keyhole. 17 years later, a different radio telescope recorded a narrow signal that lasted 72 seconds and seemed to arrive from the sky. On August 15, 1977, the Big Ear radio telescope was scanning a narrow strip of sky above Ohio. Big Ear belonged to Ohio State University and stood near the city of Delaware, about 30 miles north of Columbus. Unlike a dish that could turn toward different targets, its large reflecting surfaces remained fixed. Earth's rotation carried different parts of the sky through the telescope's receiving beam. The instrument recorded its measurements continuously, printing rows of letters and numbers onto paper. Each character represented the strength of radio energy measured during a 12-second interval. Low values appeared as numbers. Stronger readings were represented by letters farther along the alphabet. Several days after the observation, volunteer astronomer Jerry Eman examined the printout. One short sequence stood apart from the surrounding background. It read, 6EQUJ5. Eman circled the characters in red ink and wrote a single word beside them. Wow! The name remained attached to the event. The sequence described a signal that grew stronger as its apparent source entered the telescope's beam, reached a peak, and then faded as Earth's rotation carried the beam beyond it. The entire rise and fall lasted 72 seconds, which was the maximum length of time a fixed point in the sky could remain inside Big Ear's observing pattern. That timing gave the signal one of its most interesting properties. A burst of interference produced near the telescope could appear and disappear in many ways. This event followed a shape broadly consistent with a distant, stationary radio source moving through the beam because the planet beneath the telescope was turning. The signal was also narrowband. Its energy was concentrated inside one radio channel roughly 10 kHz wide. Many natural objects produce radio energy across much broader ranges. A narrow signal can therefore resemble the output of a transmitter designed to place energy at one carefully selected frequency. Its frequency lay close to the neutral hydrogen line near 1420 MHz, the same region that had interested Frank Drake during Project Ozma. Hydrogen is the most abundant element in the universe, giving that part of the spectrum an obvious scientific significance. The observation still contained serious limitations. Big Ear used two separate receiving beams that crossed the same area of sky a few minutes apart. The signal appeared in only one of them. Researchers could not determine whether it had switched off before the second beam arrived, changed frequency, or originated from interference that happened to imitate a celestial source. The telescope returned to the same region repeatedly. Later searches used Big Ear and other radio observatories, sometimes covering wider frequency ranges with more sensitive equipment. The signal never appeared again. That missing repetition prevented astronomers from measuring it with another instrument. They could not refine its exact position enough to identify a particular star, planet, or natural radio source. The printed characters contained no message to decode. They recorded signal strength over time and nothing more. Several explanations have been proposed over the decades. Terrestrial interference remains possible, although no specific transmitter was confirmed. Reflections from aircraft or space hardware have also been considered. Natural hydrogen emission has been suggested, including a later proposal involving comets, but those ideas have not produced a widely accepted solution. The WOW signal therefore remains unexplained. That word carries a precise scientific meaning. Available evidence has not established its source. The same evidence also falls far short of demonstrating extraterrestrial technology. A dependable detection would need to repeat or continue long enough for independent observatories to locate it. Researchers would compare measurements from widely separated telescopes, check whether the signal moved with the sky, examine its frequency drift, and rule out satellites or equipment near Earth. A pattern carrying recognizable information would strengthen the case further. The 72 seconds recorded by Big Ear supplied none of those later steps. Possibility appeared briefly in a paper record and disappeared before astronomy could test it properly. Future searches would need to monitor more stars, revisit promising signals, and process enough data to separate rare celestial events from the constant radioactivity surrounding Earth. By the 1990s, radio astronomy had moved far beyond the single narrow channel used during Project Ozma. Project Phoenix operated from 1995 until 2004. Its teams used major observatories in Australia, Puerto Rico, and West Virginia to examine about 800 nearby stars. Instead of waiting for unusual radio energy to appear anywhere in the sky, the project concentrated on individual stellar systems within roughly 240 light-years. For each target, its equipment covered more than 1 billion frequency channels. That represented an enormous technical advance over Frank Drake's original receiver, though the observations still depended on borrowing time from telescopes built mainly for other kinds of astronomy. The Allen Telescope Array later offered a more dedicated approach. Its 42 radio dishes stand at Hat Creek Observatory in Northern California. Computers combine the signals collected by the separate antennas, allowing the array to behave like a larger observing system and examine several regions of the sky more efficiently. A much larger change began in July of 2015 with Breakthrough Listen. The project brought together radio telescopes, optical instruments, and powerful computing systems designed to process quantities of data that earlier researchers could not have stored. One of its major nearby star studies used the Robert C. Byrd Green Bank Telescope in West Virginia and the Parkes Radio Telescope in New South Wales, Australia. Green Bank's movable dish is 100 meters across. The Parkes dish measures 64 meters across and has taken part in radio astronomy since 1961. Between January of 2016 and March of 2019, The two observatories examined 1,327 nearby stars. Green Bank observed 1,138 of them. Parkes covered the remaining 189. The search extended from approximately 1.1 to 3.45 gigahertz. A gigahertz represents 1 billion radio wave cycles each second. That frequency range contained billions of narrow channels where a concentrated artificial transmission might appear. The processing system also searched for Doppler drift. Doppler drift is a slow change in a signal's measured frequency caused by motion. The effect is similar to the changing pitch of a passing siren. A transmitter placed on the surface of a rotating planet would move toward Earth during part of each rotation and away during another part. Its planet would also travel around its star, adding another layer of motion. From Earth, those movements could make a narrow transmission slide gradually across the radio spectrum. A signal produced by nearby electronic equipment may remain fixed at one frequency, while a signal arriving from another moving world could drift by a measurable amount each second. The breakthrough listen analysis searched drift rates from approximately -4 to +4 Hz per second. Software identified large numbers of events that initially met basic signal requirements. Researchers then compared observations taken while the telescope was aimed at the target with observations made in nearby directions. A genuine signal from a particular star should become strongest when the telescope points toward that star. Many candidates continued appearing when the telescope moved away. That behavior connected them to human radio activity, satellites, or equipment around the observatories. After the events consistent with terrestrial interference were removed, 0 candidates remained. The study produced roughly 219 terabytes of publicly released data. 1 terabyte can hold hundreds of hours of compressed audio, so the complete collection represented a quantity that would have been difficult to imagine during Project Ozma. The null result still had a defined boundary. For some targets, Green Bank could have detected a continuously operating narrowband transmitter with an effective power near 2 trillion watts. The Parkes observations generally required stronger transmissions, closer to 9 trillion watts. These values describe how powerful a source would appear if its energy were radiated equally in every direction. A focused beam aimed directly at Earth could be detected with less total power. A transmitter aimed elsewhere could remain invisible regardless of its strength. Brief signals might arrive between observations, while weak leakage could disappear beneath natural radio noise. The survey therefore made nearby civilizations with loud, persistent transmitters less likely within the frequencies examined. It left quiet societies, intermittent beacons, tightly directed communications, and unfamiliar technologies largely untouched. The search had become enormous by human standards. The complete range of possible extraterrestrial signals was larger still. 1,327 stars sounds like a broad search until those observations are placed inside the full problem. A radio telescope must begin with the correct part of the sky. The Milky Way contains hundreds of billions of stars, and each target occupies only a tiny angle above Earth. Even when an observatory points toward the right system, the receiver must also cover the frequency being used. Frequency describes how many times a radio wave repeats each second. Human technology operates across a huge range, from low-frequency navigation signals to radar and satellite communication measured in billions of cycles per second. An extraterrestrial transmitter could use any part of that spectrum where radio waves can travel through its atmosphere and the space between stars. Bandwidth adds another dimension. A narrowband beacon may concentrate its energy inside only a few hertz, while a complex communication signal could occupy thousands or millions of hertz. Search software designed for one type may overlook the other. Radio waves can also have different polarization. This describes the direction in which the wave's electric field moves. A receiver that records the wrong polarization may detect only part of the signal's strength. Distance and transmitter power determine whether the signal rises above background noise. Repetition rate and duration decide whether it is present during an observation. Frequency drift changes where it appears as planets rotate and orbit. Altogether, the search depends on position, frequency, bandwidth, polarization, strength, timing, duration, repetition, and motion. Researchers sometimes describe this enormous set of possibilities as the cosmic haystack. The desired signal is the needle, while every combination of sky position and technical property forms another part of the hay. A transmitter could sit inside a star system that has already been observed and still remain undetected. Its beacon may operate for 10 minutes, once every year. A telescope that watched for 5 minutes on a different date would record silence. The signal might also fall just beyond the frequencies covered by the receiver or arrive below its sensitivity limit. In 2018, researchers estimated how much of this multidimensional haystack previous radio searches had examined. Depending on the assumptions used, the fraction resembled the amount of water in a large hot tub or a small swimming pool, compared with all the water in Earth's oceans. The comparison does not erase the value of earlier surveys. Searching one pool-sized portion can rule out certain signals within it. It also shows why decades of null results have not settled whether technological life exists elsewhere. Distance makes weak transmissions especially difficult to detect because radio energy usually spreads outward as it travels. The surface area covered by the wave grows with the square of the distance. This relationship is called the inverse square law. Move twice as far from a transmitter, and the signal reaches the receiver at 1/4 of its former strength. At 10 times the distance, only 1/100th of the intensity remains. A 1,000-fold increase in distance reduces it to 1/1,000,000th. A narrow beam changes the calculation by concentrating energy toward a specific destination. Planetary radar provides a useful human example. Radar facilities send powerful signals toward planets or asteroids and measure the faint reflection that returns. Someone located near the beam's path might detect that concentrated transmission across a much greater distance than ordinary television or radio leakage. Most everyday broadcasts spread more broadly and were designed to reach receivers on or near Earth. Some signals escape into space, creating an expanding region of human-made radio energy. The earliest experiments date to the late 19th century, while regular broadcasting began during the early 20th. Our oldest radio emissions have therefore traveled outward for more than a century. Their travel distance does not guarantee detectability. Ordinary leakage weakens, while mixing with natural radio emission from stars, gas clouds, and the galaxy itself. Detecting it from another system could require a very large instrument aimed toward Earth during the correct transmission. A deliberate beacon would be different. Its designers could select a narrow frequency, use high power, and aim the signal toward a known planet. That choice would make detection much easier, provided a receiver was watching at the right moment. Current null results place the strongest limits on persistent, powerful signals that fall inside well-studied frequency ranges. They say much less about brief transmissions, weak leakage, or beams directed elsewhere. Technologies using optical light, physical probes, or methods unknown to present science would occupy different searches entirely. Radio silence, therefore, describes the region humanity has examined with radio instruments. Large sections of the cosmic haystack remain untouched. Messages can hide through timing and distance. Large technological systems may be harder to conceal because using energy changes the light and heat released into space. A civilization can remain silent and still alter the light around it. In 1960, physicist Freeman Dyson proposed that a very advanced society might collect a large fraction of the energy produced by its star. Popular illustrations often show a solid shell enclosing the entire star, but Dyson's practical idea was closer to a swarm. Millions or billions of independent collectors could occupy separate orbits, gathering light while leaving large gaps between them. Such a project would require extraordinary amounts of material. Mercury alone contains about 330 billion trillion kilograms of rock and metal. A civilization able to dismantle planets or mine large numbers of asteroids could, in principle, turn some of that material into solar collectors, habitats, factories, and communication systems. The important feature for astronomers would be heat. Energy cannot simply disappear after it has been used. Starlight captured by a machine may power computation, manufacturing, transportation, or life support systems. Eventually, much of that energy must leave the equipment as waste heat. A warm object releases most of its energy at longer wavelengths than visible light. Human eyes cannot see these wavelengths, but infrared telescopes can measure them. An incomplete Dyson swarm might therefore make a star look slightly dimmer in visible light and unusually bright in infrared. Dust can produce a similar pattern. Tiny grains around young stars absorb visible light, warm up, and release infrared radiation. Collisions between asteroids can also create dusty clouds. Any proposed megastructure must therefore compete against natural explanations that are already common throughout the galaxy. Astronomers have extended this search from individual stars to entire galaxies. A civilization that used a large fraction of the energy from billions of stars would release an immense amount of heat. The Glimpsing Heat from Alien Technologies survey examined roughly 100,000 galaxies using infrared observations from NASA's Wide Field Infrared Survey Explorer. The survey found no clear galaxy in which technology appeared to be converting most of the available starlight into waste heat. None of the examined systems showed the extreme signature expected if more than roughly 85% of its stellar energy had been captured and re-radiated in the middle portion of the infrared spectrum. That result applies to highly conspicuous galaxy-spanning activity. Smaller civilizations could remain far below the detection limit. A society using the energy of one planet or part of one star system would disappear inside the combined light of billions of ordinary stars when viewed from another galaxy. Project Hephaestus has searched closer to home by comparing optical and infrared measurements of millions of stars. In 2024, researchers reported 7 unusual candidates from a starting sample of about 5 million objects. All 7 were cool red dwarf stars, showing more infrared radiation than expected. The candidates attracted attention because a partial Dyson swarm could produce that kind of excess. Follow-up work soon showed how difficult the interpretation was. A dusty galaxy located far behind a nearby star can appear in nearly the same line of sight. The optical telescope records the star, while an infrared instrument with lower resolution may also collect heat from the distant galaxy. Combining the measurements can make one ordinary star appear unusually warm. Researchers found that this background contamination could explain several of the original candidates and might eventually account for all 7. In 2026, observations with the James Webb Space Telescope examined 2 candidates in greater detail and found distant dusty galaxies contributing the infrared emission. Those 2 objects no longer required a technological explanation. Heat is only one possible technosignature, meaning an observable sign created by technology. Industrial activity could alter a planet's atmosphere by producing gases such as nitrogen dioxide or chlorofluorocarbons. Chlorofluorocarbons are manufactured compounds once widely used in refrigeration on Earth, and some can remain in an atmosphere for decades or longer. Artificial lighting could brighten the night side of a planet. Powerful lasers might appear as brief flashes far brighter than ordinary reflected light. Large orbiting structures could block a star in shapes or patterns that differ from the smooth, repeating dip produced by a planet crossing in front of it. Each method searches for a different physical consequence of technology. None depends on another civilization choosing to introduce itself. The absence of enormous infrared structures therefore carries more weight than a missed radio message. Though it still applies mainly to civilizations using energy on a highly visible scale. Smaller machines would be harder to recognize, especially if they were cold, inactive, or hidden among natural objects. The nearest technological evidence may not surround a distant star. It could be an old probe resting somewhere among the moons, asteroids, and stable orbits of our own solar system. A robotic visitor would not need to announce itself with a radio beacon. In 1960, physicist Ronald Bracewell described a different way for distant civilizations to communicate. Instead of sending repeated signals across light years, they might place an automated probe near another star and allow it to wait. The machine could observe planets, monitor radio activity, and respond only after a local species developed the ability to notice it. Such a probe might remain useful long after its makers changed or disappeared. Electronics would eventually fail, yet a carefully designed object could spend centuries in a quiet orbit before activating. A larger machine might carry repair systems, spare components, or a small factory able to replace damaged parts. This idea connects with the self-replicating probes discussed earlier. Biological travelers require air, food, radiation protection, and a stable habitat. Machines can tolerate longer journeys and remain dormant during most of the trip. After reaching a new system, an advanced probe could mine metal-rich asteroids, refine silicon, and manufacture copies without carrying every kilogram of material from home. No spacecraft has ever demonstrated that complete chain. Human missions reveal parts of it in much simpler form. Japan's Hayabusa 2 collected material from the asteroid Ryugu and returned it to Earth in 2020. NASA's OSIRIS-REx mission brought samples from Bennu 3 years later. Robotic vehicles on Mars can navigate, drill, and analyze rock, while experimental machines on Earth can manufacture components with limited supervision. Turning those abilities into a self-repairing interstellar factory would require a much higher level of reliability. If an older civilization sent probes into our system, several locations could preserve them. The Moon has no rain, oceans, or active plate tectonics. Objects resting on its surface can remain recognizable for long periods, although micrometeorite impacts and radiation gradually damage exposed material. NASA's Lunar Reconnaissance Orbiter has photographed the Moon at resolutions fine enough to show Apollo landing sites, but its cameras have not examined every square meter closely enough to identify every small, unfamiliar object. Near-Earth asteroids offer many hiding places. Most are known only from points of light moving against background stars. Their sizes, rotation rates, and broad compositions can sometimes be estimated from telescopes or radar, while detailed surface maps require a spacecraft encounter. The main asteroid belt contains far more objects than any fleet has visited. Astronomers have catalogued more than 1 million asteroids, and many smaller bodies remain undiscovered. A machine only a few meters across could resemble an ordinary boulder in a distant image, especially after collecting dust or suffering impacts. Stable orbital regions create another possibility. A Lagrange point is a location where the gravity of two large bodies and the motion of an orbiting object balance in a useful way. The Earth and Moon have 5 such regions, and the Earth star system has another 5. Spacecraft can remain near some of these locations with relatively small course corrections. Natural dust and small asteroids can also occupy nearby orbits, making an inactive artifact difficult to recognize from a telescope. These places have not been ignored. Surveys track asteroids that approach Earth. Lunar orbiters map the Moon, and spacecraft have visited selected comets and small worlds. The coverage remains uneven because the solar system contains an enormous volume and millions of potential targets. Most objects have never been seen at close range. No confirmed extraterrestrial artifact has been discovered on the Moon, among the asteroids, near a Lagrange point, or anywhere else in the solar system. Unusual objects have repeatedly received natural explanations once better measurements became available. That absence weakens the simplest version of galactic expansion, where old civilizations send durable machines into nearly every system. It does not exclude a small, inactive probe hidden among natural debris, and it does not show that such probes are practical to build. Their absence may reflect the journey itself. Reaching another star requires a machine to survive energy demands, radiation, dust impacts, navigation errors, and decades or centuries without repair from home. A probe, leaving our solar system, would face its first major difficulty long before reaching another star. It would need to gain enough speed for the journey to finish within a useful span of time. The nearest stellar system is Alpha Centauri. Its closest member, Proxima Centauri, lies about 4.24 light-years away. A light-year is the distance light travels in 1 year, equal to roughly 9.5 trillion kilometers. Even at 10% of light speed, the cruising portion of a voyage to Proxima Centauri would last more than 42 years. Acceleration and braking would add further time. A spacecraft traveling at 1% of light speed would need about 424 years, assuming it could begin and end the trip without slowly changing speed. Human spacecraft remain far below either velocity. Voyager 1 moves through space at roughly 17 kilometers per second relative to our star. 10% of light speed is close to 30,000 kilometers per second, more than 1,700 times faster. Reaching that speed requires an enormous amount of energy. Accelerating a spacecraft with a mass of 1,000 kilograms to 10% of light speed would require approximately 4.53 times 10 to the 17th joules of kinetic energy. That figure represents only the energy contained in the craft's motion. A real propulsion system would lose energy through heat, exhaust, imperfect conversion, and equipment operation. The craft would also need instruments, communication hardware, navigation systems, and protection for its electronics. Any mission expected to stop at its destination would require another way to remove almost the same amount of motion. The mass begins to grow quickly. Adding shielding makes the spacecraft heavier. Accelerating the extra material then demands more energy. A larger propulsion system adds still more mass, while onboard fuel must push both the spacecraft and the remaining fuel that has not yet been used. Chemical rockets handle this problem poorly because their exhaust does not leave the engine fast enough. Carrying enough conventional propellant for an interstellar mission would cause the starting mass to become impractical. Proposed alternatives include nuclear fusion engines and laser-driven sails pushed from the home system. Each remains far beyond any completed spacecraft. The space between stars also contains matter. In some regions, only about 1 hydrogen atom occupies each cubic centimeter. That density feels almost empty, yet a fast spacecraft sweeps through an enormous volume during a journey lasting several light-years. At 10% of light speed, hydrogen atoms strike the front of the craft with enough energy to damage materials and electronics over time. Charged particles can create secondary radiation when they enter shielding. The vessel might need a thick protective layer, a magnetic system that redirects charged particles or material designed to erode gradually while protecting the interior. Dust creates a more concentrated threat. A grain that would seem harmless at ordinary speed carries much greater impact energy when the collision occurs at thousands of kilometers per second. A large particle could puncture shielding or release a cloud of hot fragments. Engineers have proposed placing a sacrificial shield far ahead of the main vehicle. Other concepts use lasers to detect and vaporize, approaching grains before impact. Both approaches require reliable equipment operating for decades without maintenance from Earth. Navigation becomes equally demanding. A tiny error in direction grows across trillions of kilometers. The destination star also moves during the voyage, so the craft must aim for where it will be many years later. Course corrections consume energy and must be planned with limited information from home. Arrival creates the final obstacle. A fast probe that does not slow down may cross an interplanetary system in days. Scientific instruments would have little time to observe each world, and communication could continue for years before the collected data returned to Earth. Stopping requires a braking system. The craft might carry additional propellant, deploy a magnetic sail against charged particles, or use light from the destination star. Each method adds uncertainty and equipment to a vehicle already pushed close to engineering limits. Interstellar travel remains compatible with known physics. Its linked problems make expansion less automatic than the simple settlement models suggest. An advanced civilization could possess the necessary knowledge and still decide that centuries of effort, extreme energy use, and fragile machinery offer too little return. Information avoids many of these engineering burdens. A radio wave needs no shielding or fuel once transmitted, and it travels at the speed of light. Contact still depends on two civilizations being detectable during the same narrow period of galactic history. Radio changes the problem from moving matter to moving information. Once a transmission leaves an antenna, it crosses space at the speed of light and requires no fuel for the rest of its journey. The delay remains fixed by distance. Humanity has occupied this technological phase for only a brief period. Heinrich Hertz produced controlled radio waves in the late 1880s. Guglielmo Marconi began practical wireless experiments during the 1890s, and regular commercial broadcasting developed during the early 20th century. Our strongest early transmissions have therefore been traveling through space for roughly 130 years. Systematic listening began even later. Project Ozma observed Tau Ceti and Epsilon Eridani in 1960. The organized search for extraterrestrial intelligence has existed for only several decades inside a galaxy more than 13 billion years old. Consider a civilization located 1,000 light-years away. A signal reaching Earth tonight would show what that society transmitted 1,000 years ago. The information would have begun its journey during the early 11th century, when much of Europe was still organized through feudal kingdoms, and the Song dynasty ruled large parts of China. A reply sent from Earth would need another 1,000 years to reach the same system. The complete exchange would span at least 2,000 years, even before either side took time to interpret the message and prepare a response. The civilization that receives our answer may have changed its language, government, technology, or location. It may also have stopped transmitting long before our message arrives. This delay creates a problem separate from distance. Detection requires two civilizations to overlap during periods when one is producing a recognizable signal and the other is capable of receiving it. Suppose a society uses powerful, broadly detectable radio for 500 years. Another civilization in the same region begins listening 10,000 years later. Both may survive for long periods, yet neither encounters the other's active radio phase. The earlier signals continue moving outward as a thin, expanding shell. Once that shell passes the later world, the opportunity disappears unless more transmissions follow. Researchers sometimes describe the beginning of likely contact as a civilization's contact era. The idea connects the age of a technological society with the volume of space reached by its signals. During the first century, a radiosphere extends only 100 light-years from its source. After 1,000 years, it reaches systems within 1,000 light-years. The number of stars inside that growing volume rises rapidly, although actual detection still depends on transmitter power and receiver sensitivity. Models of this process show that nearby contact may remain improbable for several hundred to several thousand years, unless technological civilizations are extremely abundant. A young civilization can transmit successfully and still have no listening society inside the region reached by its signals. Detectability can also end without biological extinction. Communication systems may become more efficient and more directional. Modern fiber optic cables already carry much of Earth's long-distance information without releasing it into space. Satellite signals are aimed towards specific service areas, while tightly focused laser links can concentrate data between selected points. A mature society might reduce accidental leakage as its technology improves. It could reserve high-power radio for radar, navigation, or deliberate beacons used only occasionally. Some cultures may lose interest in interstellar contact, while others could transmit in short, scheduled bursts separated by centuries. From a distant telescope, each change would make the civilization quieter, even if its population and technology continued growing. The Milky Way could therefore contain many inhabited eras without containing many detectable societies at the same moment. One civilization's signals may have crossed our region before animals moved onto land. Another transmission may already be traveling toward Earth and remain thousands of years away. Timing can create isolation without requiring universal destruction or deliberate concealment. It also leaves an unresolved weakness. Short communication windows explain how civilizations miss one another, while offering no reason that those windows should consistently remain short. The chain leading to a detectable society begins much earlier, on planets where chemistry must first produce something alive. The word habitable can sound more certain than it is. In planetary science, the conventional habitable zone is the range around a star where a rocky planet with a suitable atmosphere might maintain liquid water on its surface. The boundaries depend on the star's brightness and how efficiently the atmosphere traps heat. For a star similar to ours, the zone extends across a band measured in tens of millions of kilometers. A world too close may lose water as its surface overheats. Farther out, greenhouse gases may keep a planet warm enough for oceans, until even a thick atmosphere can no longer prevent widespread freezing. Orbital position provides only the starting conditions. Venus circles its star at about 108 million kilometers, while Earth orbits at roughly 150 million. The two planets are similar in size. Venus has about 82% of Earth's mass, yet its surface temperature averages around 465 degrees Celsius. Its atmosphere is mostly carbon dioxide and presses down with about 92 times the pressure at Earth's surface. Thick clouds of sulfuric acid reflect much of the incoming light, but carbon dioxide traps heat so effectively that the ground remains hot enough to melt lead. Any early oceans Venus may have possessed disappeared long ago. Mars follows an orbit, averaging about 228 million kilometers. Ancient valleys, lake beds, and water-formed minerals show that liquid water once moved across its surface. Today, the atmosphere is less than 1% as dense as Earth's, and the average temperature is close to -63 degrees Celsius. Water remains as polar ice, buried deposits, and vapor. Low pressure causes exposed liquid water to freeze or boil away quickly. Mars and Venus show how rocky planets in the same broad neighborhood can develop entirely different climates. Atmospheric circulation matters just as much around smaller, cooler stars. Many potentially temperate planets orbit red dwarfs, the most common type of star in the Milky Way. Their habitable zones lie close to the star, so a planet can become tidally locked. Tidal locking occurs when a planet rotates once during each orbit. One hemisphere then faces the star continuously, while the opposite side remains in darkness. Early descriptions sometimes treated this arrangement as automatically hostile, with a scorched day side and a frozen night side. Climate models show a wider range of possibilities. A substantial atmosphere can carry warm air toward the dark hemisphere. Oceans can transport heat through currents. Thick clouds may form above the brightest region and reflect part of that energy back into space. The result depends on atmospheric pressure, ocean depth, cloud behavior, and the activity of the star. Red dwarfs can produce powerful flares and streams of charged particles, especially when young. A nearby planet may lose atmospheric gas over time, unless gravity or chemistry helps it retain enough protection. Habitability also extends beyond illuminated surfaces. Europa, one of Jupiter's large moons, orbits far outside the conventional habitable zone. Its surface remains far below freezing, and water ice covers the entire moon. Measurements from the Galileo spacecraft revealed an induced magnetic field, meaning Europa responds to Jupiter's magnetism in a way best explained by a conductive layer beneath the ice. A salty liquid ocean provides the leading explanation. That ocean may be tens of kilometers deep and could contain more water than all of Earth's surface oceans combined. Tidal forces from Jupiter repeatedly flex Europa's interior, producing heat that may keep the buried water liquid. Light cannot reach most of that ocean. Possible life would need chemical energy from reactions involving rock, water, and material moving through the ice. Similar processes support ecosystems near hydrothermal vents on Earth, where microbes use chemical compounds as their main energy source. A useful environment emerges from several interacting systems. Stellar energy sets the broad temperature range, while atmospheric circulation and geology shape the climate over time. Water must remain available in a usable form, and chemistry must provide raw materials with a continuing source of energy. A planet can satisfy some of these conditions for a short period and then lose them. Others may preserve stable oceans for billions of years without ever producing biology. Even the most promising environment remains a collection of matter and chemical reactions. Somewhere within that chemistry, a system must begin copying itself, changing across generations, and evolving. On the young Earth, this chemical transition had occurred by at least 3.5 billion years ago. Earth formed roughly 4.5 billion years ago, as rock, metal, and ice gathered inside the developing solar system. The earliest surface was repeatedly reshaped by impacts, volcanism, and the separation of the planet into a rocky mantle and an iron-rich core. Tiny zircon crystals found in Western Australia suggest that liquid water may have existed by about 4.4 billion years ago, although the environments surrounding that water remain uncertain. Convincing evidence of microbial life appears much later. Rocks, approximately 3.4 to 3.5 billion years old, contain layered structures, chemical signatures, and microscopic forms, consistent with ancient communities of organisms. Some of the best-known examples come from the Pilbara region of Western Australia and the Barberton Greenstone Belt in South Africa. Claims of older life have been reported from graphite inside ancient Canadian rocks and carbon trapped within zircons more than 4 billion years old. Those findings remain debated because heat, pressure, and non-living chemistry can produce features that resemble biological evidence. The early planets still contained many useful ingredients. Water provided a liquid environment where molecules could move and interact. Carbon formed flexible chemical structures, able to hold chains, branches, and rings. Volcanic gases, lightning, ultraviolet radiation, mineral surfaces, and hot water moving through rock supplied energy for reactions. Meteorites also delivered organic compounds. The Murchison meteorite, which fell in Australia in 1969, was later found to contain dozens of amino acids. Amino acids are small molecules used by modern cells to build proteins. Their presence in meteorites shows that important organic ingredients can form without biology. A famous laboratory experiment demonstrated the same principle in 1953. Stanley Miller, working with chemist Harold Urey at the University of Chicago, sealed water and several gases inside glass equipment. The water was heated to create vapor, while electrical sparks represented lightning passing through an early atmosphere. After several days, the liquid had changed color. Analysis revealed amino acids and other organic compounds. The exact gas mixture used by Miller probably did not reproduce Earth's atmosphere perfectly. Later experiments using different gases, volcanic conditions, impact chemistry, and ultraviolet light have still produced a variety of organic molecules. Simple ingredients can naturally become more complex when suitable energy is available. Amino acids remain far from a living cell. Life requires a continuing system, able to preserve information, make imperfect copies, obtain usable energy, and maintain a boundary separating its internal chemistry from the environment. Copying errors create variation. Natural selection can then favor versions that reproduce more successfully. No single agreed pathway explains how all of these abilities became connected. One major idea begins with ribonucleic acid, usually called RNA. Modern cells use RNA to carry genetic instructions and assist in protein production. Certain RNA molecules, known as ribozymes, can also speed up chemical reactions. An early RNA-like system may therefore have stored information while helping to copy or modify molecules. Current RNA molecules are complicated and fragile. Researchers still need to explain how their building blocks formed, joined into useful chains, and began copying with enough accuracy for evolution to continue. Metabolism-first models begin elsewhere. In these scenarios, networks of chemical reactions developed before genetic molecules. Alkaline hydrothermal vents on the ocean floor contain tiny mineral compartments and natural differences in acidity. Those gradients could have driven reactions in ways that resemble the energy systems later used by cells. Lipid protocells offer a possible boundary. Lipids are molecules with one end attracted to water and another that avoids it. When placed in water, many lipids spontaneously form hollow bubbles called vesicles. These bubbles can trap molecules, grow by absorbing additional lipids, and divide under physical stress. Minerals may have helped organize the chemistry. Clay surfaces can hold small organic molecules close together, increasing the chance that they join into longer chains. Iron and sulfur minerals can speed reactions near vents, while repeated cycles of wetting and drying may concentrate chemicals along volcanic pools or shorelines. Laboratories have reproduced individual parts of these pathways. Researchers can form organic building blocks, produce simple membranes, create catalytic RNA molecules, and observe chemical systems with limited forms of copying. No experiment has yet started with simple prebiotic materials and produced a self-sustaining cellular system capable of open-ended evolution. Earth crossed that boundary somehow. The event may have followed a common chemical path wherever conditions remain suitable, or it may have depended on a sequence so unlikely that most habitable worlds never completed. Once life existed here, it remained microscopically simple for billions of years. The earliest organisms left no bones, shells, or footprints. They were microscopic cells living in water, drawing energy from chemical reactions and copying themselves one generation at a time. For most of Earth's history, life belonged almost entirely to two great groups, bacteria and archaea. Archaea are single-celled organisms that often resemble bacteria in size and shape, though their cell chemistry and genetic machinery are different. Members of both groups still live throughout the planet, from soil and seawater to hot springs and the deep rock beneath continents. These organisms were already remarkably successful. Microbial communities spread across oceans, coated shallow seafloors, and built layered structures called stromatolites. Some ancient stromatolites, preserved in Western Australia, are about 3.5 billion years old. Modern versions still grow in places such as Shark Bay, where mats of microbes trap sediment and gradually form low, rounded columns. The planet remained almost completely without free oxygen during much of this early period. Oxygen reacts easily with other materials, so any small amount released into the environment was quickly absorbed by dissolved iron, volcanic gases, and exposed rock. A major change began when certain bacteria developed oxygen-producing photosynthesis. These organisms, known as cyanobacteria, used energy from light to split water molecules. The process supplied electrons for building organic matter and released oxygen as a waste product. At first, the oxygen altered the oceans. Dissolved iron reacted with it and formed iron oxides that settled onto the seafloor. These deposits became the banded iron formations now mined in regions of Australia, Brazil, and North America. Their alternating dark and reddish layers record changes in ancient ocean chemistry. Around 2.4 billion years ago, oxygen began accumulating more strongly in the atmosphere during an interval called the Great Oxidation Event. The change unfolded over millions of years and remained uneven. Oxygen levels stayed far below modern values for a long time, then increased again during later geological periods. For many anaerobic organisms, which live without oxygen, this gas was toxic. Other cells eventually learned to use it. Oxygen allows cells to extract much more energy from food than many oxygen-free chemical pathways can provide. A deeper transformation followed through a process called endosymbiosis. The word describes one organism living inside another in a lasting partnership. At some point, more than 1.5 billion years ago, an ancestral host cell took in a bacterium. The bacterium survived instead of being digested. It supplied usable energy to the host, while the host provided nutrients and protection. Across many generations, the two became increasingly dependent on each other. That internal bacterium eventually became the mitochondrion. Mitochondria are the energy processing structures found in nearly all complex cells today. They still carry a small amount of their own genetic material, and they divide inside cells in a way that reflects their bacterial ancestry. Cells containing a nucleus and other internal structures are called eukaryotes. Animals, plants, fungi, and many single-celled organisms belong to this group. Every major known eukaryotic lineage contains mitochondria or reduced structures descended from them, suggesting that this merger occurred early in their shared history. Some researchers argue that mitochondria supplied enough concentrated energy for cells to maintain larger genomes and more elaborate internal systems. That idea remains active research. Scientists still debate which features developed before the partnership and which followed it. Complex cells did not immediately produce animals. Many eukaryotes remained single-celled, while multicellularity evolved separately in several lineages. Cells began staying together after division, specializing in different tasks, and coordinating their behavior through chemical signals. Large organisms appeared much later. Fossils from the Ediacaran period, beginning about 635 million years ago, preserve soft-bodied forms, unlike most animals alive today. During the Cambrian period, starting roughly 539 million years ago, many recognizable animal body plans became common in the fossil record. By then, life had existed for nearly 3 billion years. A distant observer might have detected signs of biology during part of that time. Oxygen, methane, and other atmospheric gases can be influenced by living organisms. A microbial planet could therefore alter its atmosphere while producing no machines, artificial light, or radio transmission. Life can thrive for immense periods without developing nervous systems or technology. Even after complex animals appeared, evolution continued for hundreds of millions of years before one species began building instruments capable of listening between the stars. That outcome occupied only one branch on a vast evolutionary tree. Natural selection favors traits that help organisms survive and reproduce in a particular environment. It has no destination beyond that immediate process. A larger brain can be useful, but it also consumes energy, takes longer to develop, and makes childbirth more difficult. In many habitats, speed, camouflage, venom, or a resistant shell offers a better return. Advanced learning has still evolved more than once. Chimpanzees use sticks to collect termites and stones to crack nuts. Some populations pass these techniques between generations, creating local traditions. Bottlenose dolphins in Shark Bay, Western Australia, carry marine sponges over their snouts while searching the seafloor for fish. Young dolphins learn the behavior from their mothers. Elephants can remember water sources across large landscapes and recognize the calls of many individuals. New Caledonian crows shape hooked tools from twigs and leaves. African grey parrots can learn labels for colors, materials, shapes, and quantities. Octopuses solve containers, explore unfamiliar objects, and control thousands of suckers through a nervous system distributed partly through their arms. These abilities show that flexible cognition can arise in very different bodies. None of those lineages has built a technological civilization. Cognition alone does not create radio telescopes. A species may also need body parts capable of precise manipulation, communication rich enough to transfer detailed instructions, and social tolerance that allows many individuals to cooperate. Long childhoods provide time for learning, while reliable access to concentrated energy can support cooking, metalworking, and machinery. Environmental opportunity matters as well. Dolphins possess large brains and complex social lives, but their bodies developed for movement through water. Fire cannot be maintained underwater, and loose objects are difficult to place with precision when currents move through them. Octopuses have remarkable control of their arms, yet most species live only a few years and lead relatively solitary lives. Those traits limit the long teaching relationships that cumulative technology often requires. Cumulative culture is the process that allows knowledge to build beyond what one individual could invent alone. A person learns techniques created by earlier generations, modifies them, and passes the improved version onward. Stone tools become more carefully shaped. Spoken instructions become writing. Handcraft develops into controlled manufacturing. The feedback can accelerate once information is stored outside the brain. Clay tablets preserved records for ancient states. Printing presses produced large numbers of identical pages. Modern computers can copy technical instructions with almost no change and distribute them across the planet within seconds. Human history shows how slowly that process began. Fossils assigned to anatomically modern Homo sapiens extend back about 300,000 years. For most of that span, people lived in small mobile groups, using tools made from stone, wood, bone, and plant fibers. Agriculture began in several regions during the past 12,000 years. The earliest cities appeared only a few thousand years later. Steam engines became major industrial tools during the late 18th century, while practical radio communication arrived near the end of the 19th. The period in which Earth could produce detectable radio signals occupies less than 1/20th of 1% of our species' existence. Its arrival also depended on events that could have unfolded differently. Changing climates altered forests and grasslands in Africa. Rivers, coastlines, and land bridges influenced migration. Competition between species affected which populations survived. The asteroid impact 66 million years ago ended the age of non-avian dinosaurs and opened ecological space later occupied by mammals. Replaying Earth's history would preserve the laws of chemistry and physics while changing countless encounters, mutations, extinctions, and migrations. The resulting planet could remain full of successful organisms without producing humans or anything similar. For this reason, the Drake equation treats intelligence as an unknown probability. Earth confirms that evolution can produce a species capable of cumulative science and engineering. One example cannot reveal how often the same threshold is crossed elsewhere. Technological intelligence may therefore be rare, even on planets rich with complex life. That possibility could explain much of the silence without requiring a galaxy filled with ruined societies. It still leaves open how the civilizations that do emerge would choose to live, communicate, and use their growing power. Technological intelligence does not automatically create a desire to occupy the galaxy. Capability and motivation are separate, and the distance between stars changes what expansion can provide. A colony near Proxima Centauri would lie more than 4 light-years from Earth. Even a message traveling at light speed would need about 4 years and 3 months to cross that gap. A reply would require the same journey back. Ordinary conversation would unfold across delays longer than many governments remain in office. Physical travel would be slower. At 10% of light speed, a cargo vessel would spend more than 42 years cruising between the two systems, before acceleration and braking were included. Emergency assistance could never arrive quickly. Administrative orders would be outdated when received, and routine trade would involve goods remaining in transit for much of a human lifetime. A distant settlement would therefore need to function largely on its own. Once that independence exists, the original society gains little practical control over it. Expansion might create related populations or cultures, while producing very little of what a connected economic system usually provides. Local space already contains enormous resources. Asteroids hold iron, nickel, carbon compounds, and water-rich minerals. Ceres, the largest object in the main asteroid belt, is about 940 kilometers wide and contains a substantial amount of water ice. Smaller bodies could supply construction material without lifting it from a planet's surface. Large orbital habitats could create living area close to the civilization's home star. During the 1970s, physicist Gerard O'Neill studied rotating habitats in which artificial gravity would come from spin. A cylinder several kilometers across could hold soil, buildings, and controlled ecosystems on its inner surface. Sunlight could be reflected inside through mirrors, while shielding made from local rock would reduce radiation exposure. No habitat of that scale has been built. Smaller systems already demonstrate parts of the idea. Space stations recycle water, regulate air, remove carbon dioxide, and maintain carefully controlled temperatures. A mature society with highly efficient recycling could reuse the same atoms many times while drawing fresh energy from its star. Computation offers another possible direction. Modern data centers already convert electrical energy into calculations and release much of that energy as heat. Future societies might devote a growing share of their resources to simulations, scientific modeling, artificial environments, or forms of communication that require little physical movement. Some researchers have speculated about post-biological civilizations. In these scenarios, minds might eventually operate through engineered bodies or computing systems, rather than depending entirely on biological brains. Their subjective speed could perhaps be adjusted. A mind running slowly might experience a long interstellar delay as less socially disruptive, while a faster system could perform large amounts of thought inside a short external period. These ideas remain speculative. Science has not demonstrated that a human mind can be copied into a machine, and consciousness is still poorly understood. The concept matters because it reveals how advanced intelligence might seek richer local experience instead of greater physical territory. Compactness would not make such a civilization physically invisible. Computation requires energy, and energy use produces waste heat. Machines must release that heat into their surroundings through radiation. A society could lower its temperature, improve efficiency, and place computing equipment far from bright stars, making detection more difficult. Thermodynamics would still leave some energy signature. This is why modern technosignature research includes infrared waste heat. A quiet civilization may stop broadcasting, reduce travel, and concentrate its activity within a small region. Sensitive instruments could still search for unusual temperatures or energy use, though natural dust and cold objects would complicate the interpretation. Expansion may also lose its appeal for cultural reasons. A society with stable population, abundant local material, and vast artificial environments may see little value in sending fragile colonies across light years. Exploration could be carried out by small probes, while most individuals remain within habitats where communication is immediate and conditions are controlled. Such a civilization would violate a common human expectation behind the Fermi paradox. Growing technological power would produce better local systems rather than an ever-widening frontier. One civilization could plausibly make that choice. Explaining the silent sky this way requires nearly every civilization to remain compact, quiet, or difficult to recognize. A different explanation begins with the possibility that advanced civilizations have noticed younger worlds and deliberately left them alone. In 1973, astronomer John Ball published a proposal now known as the zoo hypothesis. He suggested that extraterrestrial societies might treat Earth in the way humans sometimes treat a protected wilderness. Observers could study the inhabitants while avoiding actions that would alter their natural development. The motive could be scientific. A civilization interested in evolution, language, or social behavior might learn more from a planet that develops without outside influence. Direct contact would immediately change the conditions being observed. Knowledge of extraterrestrial life could reshape religion, politics, technology, and the way a species understands its place in nature. An ethical rule could create the same behavior. Advanced societies might believe that younger civilizations deserve time to form their own cultures and institutions. Contact could be delayed until a planet reaches a chosen threshold, such as detecting another world independently, establishing a stable global society, or beginning interstellar travel. This proposal can account for several missing forms of evidence at once. Observers would avoid sending obvious transmissions toward Earth. Probes operating nearby could remain distant, inactive, or concealed among natural objects. Large engineering projects might be placed far from inhabited systems, where developing species could detect them. A sufficiently capable civilization might even notice our telescopes and adjust its behavior as human instruments improved. Radio emissions could be aimed away from Earth, while visible activity near neighboring stars could be reduced during the period when our observatories were able to recognize it. The hypothesis becomes difficult when its scale is expanded across the galaxy. The Milky Way is more than 100,000 light-years wide and has existed for over 13 billion years. During that time, many independent civilizations could have appeared. Each might divide into settlements, political groups, research organizations, or autonomous machines with different priorities. For Earth to remain completely isolated, every relevant participant would need to respect the same boundary. A single dissenter could transmit a message. An abandoned probe might drift into view. A distant colony could reject an old agreement, while a later generation might no longer understand why the rule was created. Human protected areas show how difficult perfect restraint can be. Wildlife reserves still experience trespassing, accidental disturbance, aircraft noise, discarded equipment, and disagreements over management. A galactic version would need to maintain far tighter control across distances where messages take years or centuries to arrive. The coordination could come from one dominant civilization or an automated system enforcing the boundary. That addition creates further assumptions. No evidence currently shows that such an authority exists, how it formed, or why it has remained effective over immense spans of time. The zoo hypothesis also faces a problem of testability. A useful scientific explanation should expose itself to the possibility of failure. It should identify an observation that would count against it. If observers are described as perfectly capable of hiding every signal, artifact, and engineering project, then continued silence always fits the hypothesis. A missing probe becomes evidence that the observers removed it. An empty radio search becomes evidence that they avoided the frequencies being monitored. Better telescopes finding nothing can be interpreted as proof that the concealment is more advanced than expected. That flexibility makes the idea difficult to distinguish from a genuinely empty neighborhood. Both possibilities predict the same quiet sky, while only one adds an unseen observing civilization. The zoo hypothesis remains logically possible. Current evidence provides no reliable reason to conclude that Earth is being watched or protected. Its value lies mainly in revealing how deliberate restraint could reproduce the appearance of cosmic emptiness. Maintaining that restraint across every civilization would require an extraordinary level of agreement. A darker model reaches silence through individual self-interest, giving each society its own reason to avoid being noticed. Individual fear supplies that motive. A civilization that sends a powerful message reveals something important before any conversation begins. The transmission shows that a technological society exists and gives astronomers a direction from which the signal arrived. Repeated observations could narrow that direction toward a particular star system. The message cannot prove what the sender will do centuries later. Interstellar communication moves at the speed of light, so distance creates long periods with no updated information. Two societies separated by 500 light-years would wait 1,000 years for a single exchange. During that interval, governments could fall and technologies could advance. A peaceful institution could be replaced by a hostile one. Ordinary diplomacy depends on frequent contact. Each side watches behavior and responds to change, allowing trust to grow through repeated interaction. Across interstellar distances, every reply describes a society as it existed generations earlier. A promise of peace may remain sincere when transmitted and become irrelevant long before it arrives. This uncertainty supports a speculative idea known as the dark forest. The name was popularized by Chinese science fiction author Liu Cixin. In the model, every civilization moves through a galaxy filled with unknown societies whose intentions and future capabilities cannot be verified. Revealing a location creates an irreversible risk. Once coordinates escape into space, they cannot be recalled. A quiet civilization may therefore avoid answering unfamiliar signals while reducing emissions that could expose its system. In the most extreme version, a society may view any visible competitor as a possible future threat and consider striking before that competitor becomes more powerful. The logic resembles a severe game theory problem. Game theory studies how decision-makers choose strategies when their outcomes depend on what others may do. When the cost of misplaced trust is imagined as the destruction of an entire civilization, silence can appear safer than cooperation. Several assumptions are required before this model could describe the real Milky Way. Civilizations would need reliable methods for finding one another, and destructive systems capable of reaching targets across interstellar distances. They would also need to believe that concealment remains possible after using large amounts of energy and altering their surroundings. Astronomers have found no evidence of a hidden network of predators. A confirmed interstellar attack has never been detected, and no known signal shows that another society is avoiding Earth through fear. The dark forest remains a strategic thought experiment and lacks observational confirmation. Humanity has already sent a few deliberate messages outward. On November 16, 1974, the Arecibo radio telescope in Puerto Rico transmitted a message toward the globular star cluster Messier 13. The broadcast contained 1,679 bits, a number chosen because it can be arranged into a rectangle with 73 rows and 23 columns. When displayed in that arrangement, the pattern represented numbers and chemical elements associated with DNA. It also showed a simplified human figure, the solar system, and the Arecibo telescope. The transmission lasted about 3 minutes and used a powerful, narrow radio beam. It was mainly intended to demonstrate the telescope's capabilities. Messier 13 lies roughly 25,000 light-years away. Any possible reply would require about 50,000 years for the complete round trip. Physical messages have also left the solar system. Pioneer 10 and Pioneer 11 carry metal plaques showing human figures and information about the spacecraft's origin. Voyager 1 and Voyager 2 each carry a golden record containing images, natural sounds, music, and greetings from Earth. These spacecraft are tiny objects moving through an enormous volume. None is aimed toward a known inhabited planet, and the chance of accidental interception is extraordinarily small. Their records function more like durable time capsules than practical attempts at contact. Debate continues over whether deliberate interstellar messaging is wise. The dark forest gives that debate its most frightening argument, though fear alone does not establish that danger exists. A galaxy-wide explanation would require many unrelated civilizations to reach similar conclusions and possess similar capabilities. A quieter possibility needs no shared strategy. Technological societies may become difficult to detect because their visible periods repeatedly end. A detectable civilization may occupy only a short interval between its technological arrival and the moment its signals fade. This possibility appears in the final term of the Drake equation, which represents the average length of time a civilization remains observable across interstellar space. Many technological societies could arise throughout galactic history, while only a few remain visible during one particular century. Humanity offers a useful example. Powerful radio transmission has existed for little more than a century. Some broadcasts escape Earth, but the strongest accidental leakage comes from systems such as radar. As communication shifts toward fiber optic cables, lower power transmitters, and narrow satellite beams, parts of our planet may already be becoming less noticeable from distant stars. Once a transmission ends, its energy continues moving outward as an expanding shell. The signal weakens as it spreads across a larger area. A receiver located along its path might detect it during a limited period, provided the equipment is sensitive enough and pointed in the correct direction. After the shell passes, the same region becomes quiet again. An astronomer who begins listening 10,000 years later does not receive an archive of every signal ever sent. Space does not hold a radio broadcast in place. The waves continue onward until they become too faint to separate from background noise. Physical technology can remain after active communication stops, though different objects survive for very different lengths of time. Satellites in low orbit encounter traces of atmosphere that gradually reduce their speed. Without correction, many eventually descend and burn up. Spacecraft in higher orbits can remain much longer, but radiation damages electronics and tiny impacts erode exposed surfaces. Solar panels lose efficiency as batteries fail, while moving parts can seize after years without maintenance. Structures on a planet face weather and geology. Wind moves sediment. Water breaks rock apart and transports the fragments. Plants enter cracks, while earthquakes and volcanic activity reshape the surface. On Earth, cities abandoned for thousands of years can leave foundations and altered soil, yet most exposed machines would corrode or collapse far sooner. Industrial chemicals in an atmosphere can also disappear. Ultraviolet radiation breaks some compounds into smaller molecules. Other gases react chemically, dissolve into oceans, or become buried in rock. Their detectable lifetime may range from years to many thousands of years, depending on the substance and the planet. Some evidence could persist much longer. Objects placed on the moon avoid rain, flowing water, and atmospheric oxygen. The Apollo landing equipment and boot prints will be altered slowly by micrometeorite impacts and radiation. Geological changes caused by large-scale mining or industry might remain embedded in planetary layers for millions of years. Longevity alone does not make those traces easy to find from another star. Earth-sized planets appear as tiny points beside their much brighter stars. Reading an ancient surface alteration across light years would require instruments far beyond those available today. A silent probe among asteroids could survive while remaining indistinguishable from ordinary rock. Time can therefore separate civilizations more completely than distance. One society might develop radio, remain detectable for several thousand years, and disappear from view a million years before another species begins listening nearby. Both civilizations would experience a sky without confirmed companions. The earlier society's signals would have passed long ago, while its remaining artifacts would be cold and damaged, blending into the natural environment. This idea does not assume that ruined alien cities actually exist. It describes an observational limit. Active technology is easier to detect because it repeatedly produces energy, signals, motion, or heat. Abandoned technology gradually loses those features and becomes harder to separate from natural surroundings. The Milky Way could have hosted many brief technological eras across billions of years while presenting only a few at any given moment. Its history might resemble scattered lights appearing across an enormous landscape, each shining for a short interval before darkness returns. If those intervals are consistently brief, their brevity may point toward a difficult transition somewhere along the path from lifeless chemistry to intelligence that can remain visible for geological time. A short, detectable lifetime may be one part of a larger pattern, somewhere between lifeless matter and a civilization that leaves lasting marks across the galaxy. One or more transitions may be extraordinarily difficult to complete. Economist Robin Hanson organized this idea in 1998 under the name The Great Filter. The framework begins with ordinary matter around a suitable star and follows a chain toward life capable of expanding beyond its home world. The quiet sky suggests that few worlds complete the sequence. The chain requires a suitable planet to remain stable long enough for chemistry to produce a self-replicating system. Simple cells then need to develop the machinery of complex cells, followed eventually by multicellular organisms. One lineage must acquire technological intelligence and cumulative culture. Its civilization must survive the power of its own tools, remain stable across deep time, and develop lasting expansion or detectable engineering. The Great Filter does not identify which step carries the greatest difficulty. It describes the effect. An ancient galaxy, without confirmed civilizations spread visibly through it. A hopeful reading places the hardest barriers behind humanity. The origin of life may require an extremely rare chemical sequence. The merger that produced complex cells may happen on only a tiny fraction of living worlds. Technological intelligence could depend on an unusual match between body, environment, culture, and evolutionary history. If one of these early transitions is the main filter, humanity has already crossed it. In that version, the silence reflects extraordinary rarity. Earth may be one of very few planets where matter passed through every biological stage required to produce astronomy. The future would still contain serious risks, but the most improbable event would belong to the past. A more disturbing reading moves a major barrier beyond the arrival of technology. Civilizations may gain powerful tools before developing institutions capable of managing them safely. Problems of coordination can grow as decisions affect entire planets. Long-term stability may become difficult when technology changes faster than laws and cooperative institutions. Human history shows vulnerability without proving that failure is inevitable. During the Cuban Missile Crisis in October of 1962, the United States and the Soviet Union moved through 13 days of extreme tension involving nuclear forces. Political judgment and communication helped prevent escalation, though several incidents brought events close to outcomes that leaders on both sides wanted to avoid. On September 26, 1983, a Soviet early warning system reported that missiles had been launched from the United States. Lieutenant Colonel Stanislav Petrov judged the warning inconsistent with an actual attack and reported it as a likely false alarm. Later investigation found that the system had mistaken sunlight reflected from high clouds for missile launches. Less than 2 months later, the NATO exercise Able Archer simulated parts of a nuclear command sequence across Western Europe. Soviet leaders were already suspicious of Western intentions, and some military units increased their readiness. Historians continue debating how close the exercise came to provoking a crisis, but the episode demonstrates how incomplete information can make ordinary activity appear threatening. Other possible pressures include engineered disease and environmental breakdown. Advanced artificial systems could create additional dangers if they become difficult to control. These remain risks rather than known universal endings. No evidence shows that every technological species destroys itself, and humanity's survival so far demonstrates that dangerous periods can be passed. The filter may also be compound. Several transitions could each be moderately unlikely, with their probabilities multiplying across the full chain. If 7 required steps each succeeded on only 1 world in 10, the entire sequence would succeed on roughly 1 world in 10 million. None of the individual steps would need to be almost impossible. That multiplication makes the silence compatible with several barriers distributed across biological evolution and long-term civilizational survival. It also prevents the Great Filter from locating the danger by itself. Future discoveries could shift the likely barrier. Independent microbial life on Mars, Europa, or a distant planet would suggest that life begins more easily than a single example indicates. Complex organisms found elsewhere would move more of the difficulty toward intelligence or later survival. A confirmed ancient civilization would show that at least one other world crossed many of the same thresholds. The framework leaves humanity in an uncertain position. The quiet galaxy may mean that we have already passed the hardest door. It may also mean that the most demanding transition still waits somewhere ahead. The position of the filter remains unknown, and future discoveries can move it backward or forward along the chain. Independent microbial life would provide one of the most important clues. Mars once held rivers and long-lived lakes. Europa and Enceladus contain oceans beneath ice, warmed by the gravitational pull of their giant planets. Any organism found in those environments would need careful testing to determine whether it shared an origin with Earth life. A truly separate origin might use unfamiliar genetic chemistry, different molecular building blocks, or another system for storing biological information. Such a discovery would show that life began independently, at least twice within one planetary system. Abiogenesis, the transition from non-living chemistry to biology, would then appear easier than a single known example suggests. The likely filter would shift toward later stages. A complex biosphere on an exoplanet would move it farther still. Atmospheric oxygen combined with gases that should rapidly react and disappear could indicate continuous biological activity. Seasonal changes in vegetation like pigments might reveal widespread photosynthesis. Finding oceans, complex organisms, and active ecosystems without technology would suggest that biology can progress far beyond microbes, while intelligence or cumulative culture remains uncommon. Each type of discovery tests a different part of the sequence. Radio observatories will continue examining more stars across broader frequency ranges. Faster computers can divide the spectrum into billions of channels, while rejecting signals from satellites, aircraft, and equipment on Earth. Repeated observations can determine whether a candidate follows the sky and returns at predictable times. Optical searches look for laser pulses that may last only a tiny fraction of a second. Infrared surveys examine stars and galaxies for unusual waste heat. Atmospheric spectroscopy separates distant light into its component wavelengths, allowing certain gases to leave recognizable patterns. More capable space telescopes may eventually produce direct images of small rocky planets by blocking the overwhelming glare of their host stars. Those observations could reveal industrial chemicals, unusual night-side illumination, or atmospheric mixtures that natural processes struggle to maintain. Searches within our own solar system can examine the Moon, asteroids, stable orbital regions, and icy worlds for biological or technological evidence. Europa Clipper began one part of that effort when it launched on October 14, 2024. The spacecraft is following a long route toward Jupiter, with arrival planned for 2030. It will use cameras, radar, magnetic measurements, and chemical instruments during dozens of close passes by Europa. The mission is designed to assess habitability rather than detect life directly. It will measure the thickness and structure of the ice, investigate the ocean beneath it, and examine material on the surface. Those findings can show whether Europa contains water, useful chemistry, and energy sources in combinations that could support organisms. Science will also become more informative as searches improve. A radio survey can exclude transmitters above a particular power within a defined range of frequencies and distances. Infrared observations can limit the number of nearby civilizations using stellar energy on a conspicuous scale. Atmospheric studies can rule out certain industrial gases above measurable concentrations. Detailed maps can reduce the number of places where large artifacts might remain unnoticed. No single null result will establish that humanity is alone. Many carefully defined null results can steadily remove specific possibilities. The surviving explanations may still look very different from one another. Technological intelligence could be extraordinarily rare. Humanity may have appeared early enough that distant societies have not yet had time to spread. Civilizations could be separated by communication windows that never overlap. Quiet societies may use technology in forms our instruments barely recognize. A difficult barrier may also lie ahead of species that acquire great power before learning how to preserve themselves across deep time. The sky does not yet tell us which explanation is correct. It does reveal a distinction that matters. The emergence of intelligence is one achievement. The endurance of intelligence is another. For now, every confirmed planet beyond Earth remains without a known technological inhabitant. Every verified radio signal has received a human or natural explanation. The only civilization known to examine the silence is the one living here. The universe may eventually answer through a signal, a fossil, an atmosphere, or an artifact. Until that evidence arrives, humanity is still deciding whether technological intelligence can become something that lasts.